Okay. One of the most important point of the composite material will be multi-scale characteristics of composite. As I briefly mentioned last time, what's the size of a diameter of the fiber? That could be like the micrometer, say 10 to the minus 6 micro level. Say a diameter. Typical diameter of the carbon fiber is about the 6 to 7 micrometer, and this represent resin surrounding fibers, and also importantly, there will be some interface between the fiber and resin system. So this yellow represents interface. So this is usually called 5 micro mechanical level. And then we can call meso level, meaning that we have applied, and of course, which consists of thousands of millions of fibers and resin system. We can call it a ply, we can call it a lamina. And also I emphasize the woven type. Woven type is the each we call woven webs, usually 0 and 90. The reason why we have a 0 and 90 is that in the woven is simply we try to make the fabrics. So each toe will have typically 20,000 fibers or 50,000 fibers. 50,000 fiber toe we call heavy toe, and sometimes 6, sometimes 12. But that is the woven or UD. This is the mesoscale, and that is the order of a millimeter, and this is the order of a micrometer. And then we make the structures, as you can see, for example, the airplane. Airplane, now we have many different layups, different angle, while that is the main issue of the design. So in composite material, design will be the shape of the outside, but inside we have layups, which we, designer, will decide it. So we, as a designer, will decide not only outer shape, but also inside the layups, which makes quite different from a conventional metal. Metal, mostly the design means that the outer shape and thickness, but for composite, not only geometric outer shape, but also we can decide it layup sequence, which makes the different material property. So composite material, we create the design outer shape, but also we create our own material property. That is the beauty of the composite material. So again, how we change the material property is to align different angles and maybe sometimes a different composite as well. For example, first layer could be a glass or carbon or honeycomb, whatever we wish. The layup will be optimally designed. Well, optimal, I mentioned the optimization of design is a very important concept in most of the design. I'd like to briefly review of the what we meant by the optimization. Anyhow, mostly structures is subject to an external load, the force, and also temperature is very important. Temperature is often neglected, but temperature could be as important as the external force, sometimes more important than the external force. So please, the temperature is the one very important point. And now force can be impact or static or cyclic or random, many different forms of the forces along with the time. So I hope you have a overview of these multi-scale characteristics. Okay, multi-scale characteristics of composites. And statically, we can think of the displacement and force, and well, fatigue life-wise, we can think of the SN curve. Okay, so now we, as you can see, we have a design issue. Design always start with given external forces. Now, the external forces are decided, but now how can we design, or how can we select the materials and the layups as a designer? Of course, we have to make this structure safe, and we have to make the structure as affordable as possible, economical view, which is also very important. And now I briefly mention here, there is it says thermoset and thermoplastic. Well, what does it mean, thermoset and thermoplastic? It's a very important plastic, two different types of plastic. So depending on the thermoset and thermoplastic, the curing process, manufacturing process from here to there will be quite different. Okay. In this here, I like to briefly mention about the one concept of the spreading of the spreading of a tone. What does it mean? Well, it means that the here we shows the fiber and resin and go on, and this woven is, as I mentioned last week, it is the made by the these very different types of tow, 1K, 3K, 6K, and 12K, meaning that each tow, don't forget please, this is called tow. One tow consists of 1K, means that 1,000 carbon fiber filaments, and 6K and so on. So 50K is the 50,000 tow. So anyhow, this is the carbon tow. So the manufacturing by selling the carbon fiber, the producer such as the Toray or Hyosung or Toho, they always produce this carbon tow. Okay, that's what they do. Carbon tow. Different number of the filaments. I will copy this one to here. Okay, so this is what they do, carbon producer. They don't know next step. They don't care about the next step. All they do is to make the carbon tow or bobbin with a different grade. For example, Toray, their grade is classified as the T700, 800, and 1100, and sometimes T300. So since the Toray carbon fiber is become so popular, and this is their brand name, classifying the grade, but this happened to be a very standard all composite society, and T700 is the standard grade, and T800 it will be about 20 or 30% higher material property than T700 in the strength and stiffness. But T800, the use is a little bit limited because it can be mostly used for the defense system, defense weapons, and the the aircraft, etc. So uses of a T800 or T1000 is somewhat limited. You have to report why you need this carbon fiber and how you're going to use that. But T700 is a relatively not much restricted, but still can be very important. Diameter, as I said, and things like that. Okay, I like to mention here one point. So the to use that carbon bobine, carbon fiber, we think about the spreading fiber poles. Spreading is the very important concept. For example, let's say each one is the fiber bobine, which I just mentioned. And then this is gonna be a spreading unit, and then this is gonna be a spread, and then you can make a unidirectional pre-preg reel. Okay, so this is the one concept of a spreading, and also this one is represented as a one toe, and then a spreading, and you can see how we make the a ply. Okay, so again, it's important to understand the concept of the toe. So before this, okay, I need to make the little bit of a figure like this, or I need to. It's good to have a bit. Oops. Okay, spread toe is the another really good, really important technology. As it means, it's a spreading is just a spread, very uniformly. Okay. The reason I'm saying is this is that okay, sorry. This is the again one toe. It can be many different number of filaments, and then this one we directly go into a weaving. This will be this guy, right? This is gonna be this guy, and now this can be go directly like that, and then you can make the spread, or spread something like that. If one toe can be spread like that, or multiple bobbin can be spread, make the large widths, such as the 1 meter wide, or sometimes just one toe, Okay, sometimes one toe is gonna be a one toe, or multiple toe will be spread. And imagine that this how this can be well spread. Well, again, just one by one, it have to be spread, and so that there should be a well spaced. But compared to this one, we gonna have a just zigzag weaving. So this is the called woven, and this gonna be called this gonna be will be just a spreaded pole. Okay, so by the spreading, the reason I'm mentioning this is that by spreading, as you can see, very typical we call ply will be, say, not always, okay, but not always, is like the 0.1 to 5 millimeter thick ply. Well, again, this widths can be any widths as we wish, but typical ply or this can be many spread. I mean, many number of toes. And then we can have a plus resin there. Then it is called pre-pregnated, so pre-pregnated, meaning that resin is already pre-pregnant. So in short, we call pre-preg. Pre-preg means that now you need to, now you can imagine that how they pre-preg are made of. Like this, starting from this toe and spreading, and then you have some resin system, and then you make the pre-preg. And now woven is not just no resin yet, so you need to have a resin there. How? Well, there could be many different way of impregnate or insert resin there. So dry carbon fibers and dry carbon fibers, and in some of you have a resin there. So this gonna be a pre-preg, or one toe can be and the resin can be impregnate many different way. So back to this multi-scale approach. Imagine that you have seen many times about this ply or woven. Now you can imagine how this is made of. Thousands of fibers, each toe, and weaving. And now this kind of very straight, okay, very straight a ply, unit ply. Now you can imagine how this is made of, which is by spreading fibers. So spreading fiber sounds easy task, but it's not that easy. All the quality of the pre-preg and the quality of the ply is coming from spreading technology. So I hope you understand where we are. As you can see, you know, we have a bundle of the roving, or you can imagine the one toe. Okay, one toe again means that we have a 20 1,000, 10,000. You just, I hope you visualize them, how many filament we have. Now we like to have a spread, the spread very much uniformly. How we do that? Well, one way it shows here is that airflow. We have airflow like an air blow, and then it makes this one is very much spread in horizontal direction. Okay, so as I show here, one toe comes here, and there will be one roller, and then there's can be special airflow, and there can be very special heat. We apply somewhat heat. So and then a vibration, So one toe, as you can see, I like to emphasize this go over roller, and there can be some airflow or heat, or sometimes the little bit of a humid. I would just call it watering. And then of course very important is the tension. So it's not just one step, very different steps of the roller, air, heat, and water, and go on, and then now we can reach like the point 1 to 5. Why 1 to 5? Did I pick this number arbitrarily? No, this is a very typical, the thickness of one ply. So this can so finally we can have a one ply. Okay, so again, this is gonna be the same thing. Just imagine over here, this will corresponding to here, and then here very important is the impregnation unit, very small here. But impregnation unit means that you add a resin here. So you have a resin here. So this is already pre-pregnant, okay, pre-pregnant process, and this is just the one step over here. And then this is also important. Why? This can be a method to produce the toe preg. Why they call toe preg? Well, toe means the one toe, and then preg means the pre-preg. So resin is added to a one toe. That's why you call it toe preg. So toe preg means the one toe with a resin there. And pre-preg is just a multiple toe preg and spreading, and then we have a resin there. Okay, now resin can be, this resin or whatever resin can be, have a thermoset or thermoplastic. Very important classification of the plastics. We will certainly go to that issue. So this thermoplastic or thermoset, same for here. We have this is a dry. Now to make the composite, we have to have some resin. Resin can be thermoset or thermoplastic. Okay, so this is the microscopical understanding of the composite starting from the toe. Okay, this is the one toe. And here I like to go a little bit more in detail about this 125 and millimeter and ply. And again, this starting from, I like to use the other slide here. Again, Oops. Oops. Sorry. Here. So the it's better start to actually here. So the this is the one carbon filament times whatever number of filament and goes here. And this diameter, okay, this diameter, as in mentioned here, it can be 6 to 8 micrometers. You may wonder now as a prime level, we have a 0.125. I like to count. Okay, I'm gonna use the previous these pictures again. But it just represents the one pregnant prepreg. Okay, now each toe has some dimensions. Okay, like this. I hope you keep visualizing how this is made of. So as I said, this will be a very typical thickness as the 0.125 millimeter. And this one I mentioned about this gonna be about the 7 micrometer. Now, we like to understand how many fibers through the thickness. That's what we like to understand. So this is the simply 125 micrometer. So if the fiber is well arranged like that, just approximately, okay, just like that, and again the 7 micro, and then how many fiber filament should be stacked up to reach this one. You can see it's about where anybody can calculate. 18. Right? 18 filaments of this carbon fiber. I just simply 125 divided by the 7 will be 17.8 or 18. Okay, this is how I got this number, 18 filament. So when you have a prepreg, now you can visualize we have about 18 filaments of this guy, and imagine that we have one toe, okay, one toe, very difficult. Let's say 24,000 K, like that, and this gonna be a spread, and vertically we will have 18 filaments to make up to have a 0.125 millimeter. Now, here, let's try to have then how much the width we can have from one toe with this thickness. Can you calculate it? So imagine, see, we have a 24,000 toe. Now we have 18 filaments, and you can imagine how many. We just assume that all fiber is arranged in rectangular pack. So 24,000, right? Divide by 18. And then we will have 1,000, about the 300, 1,300 filament in now this will be let's say divide by 7 micrometer, 7 micrometer. No. Multiply by the 7 micrometer. Okay. And then in terms of millimeters. Oops. Now you have about the 9 millimeter. I hope you understand what I'm trying to do. This is gonna be a 9 millimeters. Okay, so one toe, 24K. Each toe, each fiber has a 7 micrometer, and then we spread vertically. We will have 18 filaments, which makes the 0.125 millimeter. Now, very important issue will be the width is about the 9 millimeter. Okay, so the 24K toe will be 0.125 millimeter thick and times 9 millimeter. That is the about one toe. And now to make 1 meter long pre-preg, you can see how many toes we need. How many toes we need. So this is gonna be a like the 9 millimeter will be about 1 centimeter, and then to make the 1 meter, you need 100 toes to make pre-preg with a thickness of 0.125. Okay, so this one you can have just alone. So this is gonna be a toe preg. Dimensions of the toe preg, and I need to have this one to come. Okay, this is fine. Okay, so I hope you can visualize these dimensions. While in general, as you know, the visualization makes very important for engineers to better understand our behavior. Now you can see this is the well spread, straight, okay, rather than just the zigzag woven. And now you can see how this is made of and how this is made of. And then you can imagine how much the thickness and the width from one toe and this woven. Now, as mentioned here, we have a choice of the many different number of fibers. Let's say 1,000, 3,000, 6,000, and 50,000. So as you can see, 1,000 compared to 1,000 to 50,000, there's a 50 times more productivity, right? 50 times of productivity. But the 50 times and the quality of the toe or quality of each carbon fiber is the not as good as a low carbon, low toe, a low number of filaments. So heavy toe, this is a 50K, which is the much cheaper than 24K, even for per weight. So which is the very important to understand. So the this is the number of toe, and this is the dollar per kilo. Okay, please pay attention. This is the dollar per kilo, and low. This is the 1K or 10K or 25K or 50K. The price per kilo, okay, price per kilo will be significantly dropped. Like this. I would say more, very much drop. So sometimes the 24K and the 50K is almost the double price. Not double, is a very like the this price will be about the 70% of this or something. So which means that in terms of a price, this is a per kilo. Okay, means that we have a one toe. Okay. 24 times of filament, and this one like the 50 times of a toe. Imagine these two toe, the price will be the same if this is the 50% cheaper. Cheaper means that in terms of a kilo, dollar per kilo, and one toe, they will be the same price, right? 25K or 50K. So that's why, but the material property in terms of stiffness or strength will be, material property will be unfortunately dropped as well. Okay, so dropped as well. So something like that. Not much, but something like that. Material property. So as you can see, the performance per kilo, this is good. But the performance, absolute performance-wise, this is really good. So this guy can be usually used for very special purpose, like the PCB, the printed circuit board in the electronics, and they need a very thin layer of the carbon fibers. Then they are using this one. And this one is a relatively cheap, and even with a lower material property. This is for the wind turbine blade. And 24K, while the cost is okay, material property is okay. So this is very widely used, very much standard number of tone. And this is the very special purpose. It's not just one, it's a 10K or something like that, okay? So the, speaking of the wind turbine blade, okay, speaking of the wind turbine blade, $50K we call a heavy tow. And the wind turbine blade is typically made of the skin. Okay, this is the shows the cross sections, and this is the upper skin and lower skin. And we have a very important structure is called spar cap. Spar cap. Okay, this is a shear web. And spar always represent the vertical things, and spar cap is the long width plate. Maybe this one is better. Okay, this is a spar cap. This is all made by the carbon fiber, and other skin like this, other skin is made of the glass fiber. Can be cheaper. And the spar cap is made by the carbon fiber. And why? Because this will carry most of the load and top and bottom. And so the but spar cap, imagine that how much we need. Man, is a huge. You can imagine that this is a truck and transportation of one blade, and you can see how much the carbon fiber in there, the pre-preg, tow preg. So I will just add here for your reference, and the spar cap will be used for the tow preg 50K heavy tow. And now this width of the spar cap is sometimes I would say 50 centimeter, and the thickness will vary along the blade. So it all depends on the design. Well, we can discuss a lot about the wind turbine blade, which is very interesting to a designer like us. Okay, but next time we cover about the wind turbine blade structures. But anyhow, the point is that the 50K is the lower price and a little bit less material property, but the performance-wise is cost performance-wise very good. And then it can be used in very big structures. So I like to draw another line here that say we can have this one. This is the cost effect. Cost effective means that doesn't mean giving us the best, better property, but in terms of cost. Okay, so I hope that I just wanted to give an idea about this fiber and resin, and then up to here. One thing I briefly like to speak about the woven. Woven is very widely used as well, but the how the woven, I would say, fabrics made. You can see this is very similar to your fabrics. Okay, just one the what we call warp and the woven. I'm sorry, warp and webbed. Where is the webbed? Okay, they call filling yarn, but imagine that each yarn, okay, is yarn, and this is a yarn. It is a one toe. So now you can easily imagine that, oh, how this guy is made of. The it is the I'm sure we will have a video here how this guy I hope this one had.
Hi, I'm Steve from Fiberglass.
No.
Today we're going to take a look at our most popular carbon fabric, our 1069 2x.
These guys is trying to introduce the how we use the woven fabrics. I'm sure he's gonna introduce how to impregnate the resin in these dry fabrics. But the what I like to show weaving method. Do they have any weaving method?
Hi, Paul Anthony Composites, and today we're going to be looking at carbon fiber themselves.
Well, he introduced many different woven, as you can see. This is the see, for example, this guy, this one, this is a one spread it very well spread it and then weaved like this, and more spread, and this is a without spread. And as you can see, there are many different forms.
But honestly, it doesn't need to be. In this video, we'll take an overview over all of the most common types, weave styles, and
so as you can see, okay, so they just show all the as you can see, the weaving pattern is a little bit different, right? This is called tool weaving pattern. Depending on how warped and webbed interlocked, we give them a name like the tool or plain or satin, something like that. So we will go back that point again, but I hope we understand the toe press. I mean the weaving woven. For example, like the like this. This is very much plain weaving and tool weaving and satin weaving, depending on, as I said, up and down and up and down. Well, just for your reference, we can model them using our computer simulations. And this is a plain and tool, and then harness satin, and many different names. And then we can geometrically model them as the like this, and we can see just a number of interlock. We can generate many different types of woven patterns. But keep that in mind, each one will represent a toe, and each one toe means that it can be a 24K or 50K. Okay, so this is the something about the woven. Woven is the well used in aerospace and automotive as well. Okay. And I want to, just 1 second, please. There must be something. Sometimes this technology is very much confidential. They don't like to show. Okay, I found this one. As you can see, okay, it doesn't move, but you can imagine that each one, you see, this is a little bit wide, which means that each one is already a little bit spread. This is a new technology. A company startup this technology, and one goes here and the other go here. I hope they are showing some movement, but you can visualize each toe will come to many different warp and webbed. So it's exactly the same as the producing your fabrics. Okay, this machine is very complicated, but you can imagine that. I hope you something moving process. Okay, maybe this one. Yes, like this, like that. You see, something like this. This is how we make the woven. Well, I'm sorry, this is not the woven pole, but the machine will be very much same. I hope you understand what I'm trying to say. And also, okay, this will give us some a little bit of visualizations. And okay, this is the machine I'm talking about. And as you can see, you comes here. Weaving process is the each one again start with the one toe. I mean one bobbin, and then one toe will come like that, and then lots of machine. We have a weaving machine, zigzag weaving machine, and then we make the like that. And then this one is the woven. So you can see wove and webbed fibers, and then you can see how they are interact. The good thing with this woven is that you can have a fabric form without resin. Okay, without resin is gonna be already a fabric form. So it can be used, well, this doesn't show the carbon fiber, but the very same as in the conventional process of flow. This is the typical close, right? But again, the woven is the same technology. Well, I can see woven a girl working with a bamboo. This is the same. This is the same. I'm sure that this will be the same one. Well, I cannot say what she says, but you understand. Each toe will be zigzag and then interact and make the fabrics. Okay, so right now I wanted to cover what do we mean by this level, pre-preg, flat, and then woven, starting from the fiber and toe, and so on. Okay, so the key point is the how we have the resin there. Okay, so whenever you think about the composite, I hope you visualize how these tow and fabrics are made of, starting from the carbon and the filament. Okay, this is very important visualizations, and then we can move to our next. Okay, let's have a 10-minute break. Okay, we just briefly introduced, hoping that you can visualize the composite structures when you design composite structures, how these structures is coming from fiber and resin system and micro and macro level. And this is a spreading of toe is a very important concept. We can make the woven and pre-preg and etc. And toe preg. It doesn't have this is the one toe, and with the resin it will have a toe preg. Okay, toe preg, and this is a pre-preg. And this is a one concept of a toe preg, or yeah, this is a one toe preg. Speaking of the toe preg, now is becoming very important. Conventional pre-preg is being widely used, but toe preg is getting important. Well, I can Now, next one, very similar to our previous multi-scale overview with a different just name, hierarchical multi-scale characterization of composite. At the bottom, this kind of pyramid hierarchical structures will also help you to visualize the how the composite structures can be designed and etc. And again, the micro scale level, we call constituent. Constituent means that a fiber, resin, and interface. And then this make up a ply. And now you now understand this is a one toe. Toe again is a 24,000 fibers. And this one ply, you can see that it can be spread. This can be spread, you can have this one. And then now each toe can be used to make this kind of fabric. And also not just this is the woven plain fabric, but it can be a braiding or it can be stitch. So I will cover this one. And then we can have many layup, and then finally we can make structures. One point I like to make the comment, very important comment, is the blue line. Blue line means a blue arrow is the stiffness. So the composite, when you design a composite, we need two concepts always: the stiffness and strength. And stiffness means that how stiff or how soft the structure is. So the ply or toe stiffness will come from the fiber and resin and the fabrics, stiffness and laminate and up to here. Now under structure, under load or under temperature, there will be a high stress will be developed. You can imagine how much stress will develop. And once we have a stress or load in each cross section, each stress will be carried by the laminate or carried by each fabrics and ply. And imagine all the load are carried by eventually by the fiber and resin and interface. So now if too much load applied to composite, you can see how much the load can be carried by the fiber and resin system interface. Well, fiber and resin have their own stiffness or stress strain curve. So if too much load in there, what will happen? Well, material will simply fail. And then our material property will degrade. Once the material properties degrade, we are losing the stiffness, and then our material property will affect the ply and fabric and laminate and global. So what you see as a global designer, only this part, but now you as a composite designer, you need to visualize what will happen, what would happening in the composite. And not just for the static, but also fatigue as well. Fatigue, you have a lot of cyclic or random load here. So, whatever stress developed will be transmitted or carried by the laminate and fabrics and ply and fiber and resin system. So resin system and the fiber system, or resin can be thermoset and thermoplastic, has its own SN curve. So imagine how much the load will be cyclically applied to a fiber and resin system, and they have their own SN curve, and then it would have a certain life. And after a certain cycle of load, the composite will degrade, damage, or fracture or fail. That would affect all the stiffness. And once some part somewhere the damage is progressing, material property will degrade or changing, and then this global KDF means that K, what does it mean? Always the stiffness. F, what does it mean? Is the external force. And D is what? The displacement. So displacement will cause a strain and stiffness and stress and this kind of cyclic overview. We as an engineer, now we need should be able to visualize whatever we do as a design of global structures. Okay, now here, as I mentioned, I like to focus on a little bit about the toe preg. This is the toe preg, okay? Toe pre-pregnate. So toe with the resin system, toe resin system, toe preg is become very important. Why so become the important? There could be many reasons. The okay, we can find the back to here, and the toe preg, carbon fiber. Okay, see, we like to focus on one toe and one toe preg, not like the whole pre-preg. So one toe will represent for example, this one is the this looks similar to a fiber bundle, but this is a different. This is the fiber. Now it has a pre-pregnant resin there, so we call toe preg. Okay, remember this is the resin is already there, which will be different from this. Okay. And this can be used for example, the like the laminate. Well, sorry, I'm looking for a certain. Okay, I just like to emphasize that the toe preg is again each toe, each one has now the resin is already pregnant, and you can see how many there, and this can be used to make the airplane and Okay, sorry. I will get back to that point very soon. So this is the tool, and then now as a designer, we like to develop a composite part. With understanding of all the composite microscopic overview and understanding global view, but there are not many composite designers all over the world. We are a lack of the designer. And I'm sure that if you, as a designer of composite structures, you will be very unique engineers. You know, engineer, what make you engineer so special? You need to have a technology. Then you can be even more important than any person, you know, composite, special. You will have a very important role. And again, the composite is getting widely spread all over the world and all the structures. I don't need to repeatedly mention that, but it's gonna be a huge, you know, the applications. I mentioned. You know, the airplane, automotive, and sports goods, you name it, everywhere. Everywhere we have so much applications. Why so composites are so special? Well, now you can visualize that, you know, you composite has made of the so much small diameter of fibers and make the whole structures are so strong and so durable. The life will be so long compared to metals. Why? Because when the composites has the certain load, the cracks can be easily propagate. But the composite, I mean, in metal, the crack can be easily propagate, but the composite, the crack can be easily stopped by the small fibers and the very light. Okay, so very special. But again, nevertheless, why there are so limited composite engineer? Well, we as the design of a composite structure is not that easy. Not that easy. Why? Because the unlike the conventional metal, we have we could have many different angles, layer, and choice of a fiber and resin system. That give us a lot of choice and freedom, but at the same time, we as a designer is kind of difficult to analyze them with the whole understanding of laminate theory and etc. And at the same time, the cycle time or manufacturing process to design, we need to understand manufacturing process, such as the compression molding, injection, and the resin transfer molding, and RIM, and the CR, so many different RTM and filaments, and many different process, even through tape layering and robots. We need to understand manufacturing process. We need to understand the composite behavior, and we should be also able to select the resin system. Sometimes the thermoset and thermoplastic, and sometimes the we have to consider material cost, and we also have to consider the recyclability or processability and many different forms. So and cost is also very important. So again, in short, material is very so many choices, and we have to consider the cost. And designer, we have to understand the layup sequence and understanding anisotropic behavior. And manufacturing process can be very much different depending on the structure. So we as an engineer, composite engineer, we need to understand material behavior and design and manufacturing process. Now, with all this experience, I mean, you cannot be perfect, but you as a unique experience in each field, now you as a composite designer will be very unique. Wherever you whatever job you have, whatever role you have, you will be treated as a, you know, thing. So you can control your life, you as a composite designer. Trust me, there are not many composite engineers out there, not just in Korea, not just in China, and Europe and India. There are a lack of the composite engineer. So many companies are looking for a composite designer or engineer, but there are not many. Why? Again, there are many things you need to cover them. And conventionally metal structures, we have a different divisions. Like one division is for the manufacturing. So these guys just working on the manufacturing. One division for the design. They don't just the design. One division for the material understanding and material characterization and material procurement. So conventional company has each division and role and department. Now composite, while you engineer have to, there cannot be a separate role. We have to understand them. That's why the company has problems in terms of maintaining engineers and maintaining, administrating all the tasks and so on. But again, you as an engineer, you should make yourself strong. You need to understand material and design and manufacturing. Open to them, and then you just combine them. Well, you're gonna be very unique. A lot of company will welcome you. So trust me on that. Anyhow, I already mentioned about the multi-scale simulation of a composite a little bit. Again, now you could have a better understanding what do we mean by the ply, what do we mean by all the fiber and resin, and what do we mean by the fabrics, each toe. And virtual manufacturing means that, using this material, using this material, and through design, you have to manufacture. But manufacture change the form of the composite, like the draping, as you can see, all the toes, angles are changed, right? That used to be a 0 and 90, but depending on the form, you are changing. So let's say you have a toe crack, laminate, flat laminate, and then make a shape, then our shape will be changed. And also a draping, this is a draping and RTM. We have a dry fabric, and now resin will flow. And how we make the resin flow effectively, we need to understand the resin transfer molding. And whatever things, the structure will be cured. Once cured, the structure will have a history of a temperature and history of a curing process, which will cause the residual stress in there. How much residual stress will be created and generated inside the structures. So which can make the shape changing a little bit like this. So we need to understand these things. So we can call them virtual manufacturing. And performance is the impact and fatigue behavior. So when we understand the impact behavior or fatigue behavior, now I repeatedly emphasize that what will go on inside the structures. Okay. I sometimes repeating the content. Now this one is the again carbon and thermal set and thermoplastic. Now I like to little bit pay more attention to thermal set and thermoplastic. You know, the all the resin system, the manufacturing process is mainly, you know, this manufacturing process of this is mainly determined by the choice of a resin system, thermoset and thermoplastic. Okay, so understanding of thermoset and thermoplastic is very critical. So the we have this is the we already covered the carbon fiber. One thing I like to emphasize is that I'm sure you heard a lot about the graphene or CNT, and well, they are all carbon, you know, but the only difference is the layer is different. It's a graphite. So this one is the layered like this, and layer and layer and layer and layer, which makes the carbon fiber in this way. So you can imagine that, you know, like the one layer makes this one. And it can be very strong in this way, right? You heard many times the graphene. Graphene is like a flat type, and the carbon nanotube is like the CNT, is the like the cylindrical shape. That's the only difference. Now, graphite means that we have a multiple layer of the graphene. You can easily imagine like that, and you can imagine how many layers like that. So you can see that it can be very strong in this way, but it can be weak in this direction, in transverse direction. Why? Because this is a layered layer, and this can be separated. So this is another feature of the graphite and the carbon fiber. Carbon fiber can be weak in transverse direction, but relatively very, very strong in fiber direction. So production of a carbon fiber is to align these atoms and this carbon in a way of this strong direction. That's the one thing we need to keep that in mind. The well, this is the carbon fiber, one of these, and one of these, and one of you know, these. There are 25,000. And you know, you compare with the human hair, is easily visible human hair compared to carbon fiber. So that's why the carbon fiber is so small and it cannot easily visible. So the carbon now composite material preform and laminate process. What does it mean? Carbon fiber doesn't mean always the continuous. Can be a chopped fiber and short fiber and long fiber, and also can be woven fabrics, and also stitched in NCF. We call NCF. What does it mean, NCF? We will cover that one. And pre-pregnate is already resin there. So you can, but no matter what, we always start with this bobbin. Okay, this is the, let's say, 24K, and then we have 24,000 of fiber and one toe, and then we chopped, and then we have a carbon fiber chop and a short fiber and long fiber. Well, this is the glass, not like the carbon, but a similar concept. And then a layer and process and things like that. So one thing, important point is that the between the glass and carbon. We just emphasize the carbon fiber, since carbon fiber is very strong, very unique, very widely used. But pay attention to these characteristics of a carbon fiber. Is a density is about the 1.7, and the Young's modulus of fiber itself 2020 or even higher. And the pristine strength, what does it mean? Pristine strength means that one fiber strength, one fiber strength like that is the 45 or 4,500 megapascal. Okay, this is a megapascal, and this is sometimes 5,500. I hope you memorized this number, 2020 gigapascal, compared to steel. Steel is about 200 gigapascal. Fiber alone, the Young's modulus is higher. And failure strain is also important. Failure strain, you can simply divide by the strength, divide by the Young's modulus, giving us a failure strain. Failure strain, this number, like the 2.0, this one, you will see how important this number is, because all the fibers are glued together and deformed together. Even though it's a glass or carbons and different, they are all glued together by the resin, and then they deform together. So it's difficult to understand how much is stress in there, but no matter what, the strain will be the same. So understanding of the strain is important. Now here, the material cost compared to e-glass. Glass is this is a very standard glass. Glass, their material property is good, but relatively the stiffness is low and the strength is low. But good thing is that the failure strain is large. It means that you can extend before the failure. And we have a special glass like R glass and S glass. And the material cost with respect to E-glass, you can imagine about 10 times more expensive than E-glass. And the stiffness or weight can be only 25% compared to E-glass for the same stiffness. And then recently, the recycling of carbon fiber become very important. So even this carbon fiber as a virgin carbon fiber, or how many recycled carbon fiber, the material property may change. So that is also a very important issue. And now, speaking of the glass and carbon fiber, I like to emphasize that diameter of the carbon fiber, again, the 7 micrometer, and diameter of a glass fiber is almost twice. So something like this, and this guy is something like that one. So cross-section wise, you can see how much wider cross-section. Now, because of this guy, because of this wider, bigger cross-section, which give us a really good, makes the behavior differently. And now I like to say that tension and compression behavior of glass, the blue represent the, sorry, oh yeah, glass, oops, okay, sorry. This is a carbon fiber, and this is a glass fiber. And you can see the tension property. We have 3 different tension behavior. Why? Depending on the manufacturing process. This also makes the situation difficult for the designer. Well, even one carbon fiber, the material property, I mean, this is a carbon epoxy. resin is already there, okay? Depending on the situation, depending on the curing process, the material property can be different, but not much. Within plus minus 10 or plus minus 20%, you can see that this is the average properties. Now, compared to glass, the tension, again, different material property depending on the situation, and you can see that this one can be very different, almost the half, almost twice higher than glass. But compression behavior compared to this glass is almost the same, compressive strength. So let's say this is the composite. Let's say you want to use the composites for only for the compression. Which fiber you want to choose? Well, no reason to choose the carbon. Carbon is expensive, so I'd rather choose the glass to support the compressive. So the material property, you have three different properties. Is the depending on the how you make the infusion, is the a little bit lower strength and pre-preg, and then a higher pre-preg is giving us the better property. So this is the I mean, you don't have to remember all the number, but I hope you understand the behavior of the carbon and glass. Now the question: why carbon fiber is the stronger in tension and weaker in compression? Well, that is related to a size of a filament. The carbon is a 7 micrometer, very, very small diameter, and glass is a little bit larger. So tension-wise, well, the behavior will be divided by the cross-section is similar, and then the carbon itself is stronger than this is stronger. But now the situation will be different under compression. Compression is the not just the material property, but the structural behavior of the fibers. Meaning that if you have a very small diameter under compression, that could be easily buckled. So as you can see, very low compared to, not low, but low compared to tension. And another thing, why this is the weaker in compression is that you can imagine this one. The compression is this layer is a layered layer, and this relatively is weaker. And then on the compression, there can be a little bit separate easily. So that is the another one. Then you may wonder, okay, if small diameter is not good for the compression, why there are people, why they make the small diameter of a carbon fiber? Why they want to make the small diameter compared to a large diameter of the carbon fiber, let's say 20 rather than 7? Why is that? There's a very important features like the small or larger. The beauty of the composite is that under tension, let's say we have a crack there, crack propagate, crack existence is the same probability. So if we have a larger or smaller, then the same probability of a crack. The larger, if we crack, this one can be easily broken, right? So that's why the smaller diameter is much preferred in terms of in increasing the tension. So tensioning load, you choose the small diameter and carbon fiber. Compression, well, is a questionable. So carbon is considered as not good for the compression in general. Okay. this is the not the exactly the same behavior, but I like to help you to visualize what would happen in the tow fiber. And this is a tension and compression. This tension is is higher than compression. And imagine we have a lots of a fiber there, and lots of a fiber is not, they are not straight. They could be sometimes undulate and curved. Okay, so what if it is the compressed? Tension will be strong again, but the under compression, as you can see that compress, each carbon can buckle and then break. Well, this is all simulation through abacus, but you can see under compression, the behavior will be quite different from a tension mode. So that's the one thing we need to understand and locally. Well, there is another behavior like the kinking or global buckling behavior, but this material-wise, this could happen. Okay, so I just mentioned about the compression, difference between tension and compression. Now we can think about the hybridized fibers. You know, this with a different fiber size, large and small. As you can see, if the packing of the fibers is the nothing to do with the diameter size, because this is the no matter what the size of a carbon fiber you have, about the 50%. But if we combine them, different size of a diameter, and then these small fibers can fill inside the large, and then this is the way we can increase the fiber volume fraction. Well, this is just the better understanding of the carbon and hybridization and so on. So if we hybridize, the stress strain can be controlled depending on designer, and also we can analyze what will go on between what can be what kind of stress will distribute depending on the fibers and things like that. See, if we combine them, the longitudinal tensile and the longitudinal compression, and we can optimize the many different local behavior of composite things. And even the CAI, compression after impact, this is also very important behavior. Compression after impact, CAI. So while this is just the my proposal, okay, this hybridization of a carbon fiber and things is not fully commercialized that, but to commercialize that, you know, we can combine two different toll and process. So anything you can imagine can be a visual. We can process. Okay, now I'd like to emphasize about the thermoplastic and thermoset. We need to understand thermoset and thermoplastic to better understand the manufacturing process. And the okay, in general, okay, not always, okay, in general, thermoset. Thermoset is the thermal. I can say, I can separate this word. Thermoset. Thermal means that heat up, temperature increase. Is a set means that it's solidified, it's secured. Okay, thermoset. And now thermoplastic, what does it mean? If we apply the heat, it becomes plastic, more plastic, and more ductile. So the thermoset and always the long time is needed. Time is needed. Why? Because the thermoset is the relate to a chemical reaction. Chemical reaction is the it takes time. You know, epoxy, polyethylene, and vinyl ester, and PO. They are all thermoset. And chemical reaction, you know, all the polymer chain, they would have a interact, we call cross-linking, which makes it very strong. So long polymer chain, they will have a cross-linking, and they just become a one solid, one part. They cannot be separated by the chemically or mechanically or by any heat. So we need to apply the pressure and temperature, but very important, we need to apply long time. Why? Because it takes, the chemical process takes time. We have to wait, okay? So always a pressure and temperature, but we have to wait. So relatively low temperature, relatively low pressure, but the most important point is the time to cure. So the cross-linking takes time to bond them. Now thermoplastic, okay, I may go to, oops. Since we have a multiple nationality, I like to say the thermoset. So thermoset is the, you know, the 열 means thermal, and set means 경화. 경화 is the hardening. So the, let's say, I'm gonna change the, Chinese. And as you can see, thermal means that 열, right? This is a 열. 경화 or 고체, and 성 is a characteristics. So thermoset, I hope you don't forget this word. And thermoplastic, sticks. See, thermoplastic means when you heat up, well, I'm sorry, I cannot fully explain. This looks a little bit. Okay, so this is the showing the property like the melting, right? Melting characteristics. So thermoplastic, you become melting. And so thermoplastic means that this is all the polymer chain, individual polymer chain or crystalline or some certain structures. Now, to make them entangle, not chemical bonding, but entangle, like the spaghetti. Spaghetti, they are not bonded together, but the long chain is entangled. Entangled makes it very strong. So we need a very high temperature, very high pressure, very short time. So thermoplastic, you need a very high pressure and high temperature, and the time can be very short. Okay, this is the, but the most important characteristics, the temperature and pressure. Time can be very short. But the thermoset, you have to wait until all the chemical process. So this is the brief characteristics of a thermoset and thermoplastic. Now this represent of the thermoplastic PP. The bottom one is cheaper and lower property, and upper is more expensive and better performance. So PP and PA6, acrylic, and PA11, and PAHT, and PVDF, and PEG or PEEK, polyethyl ketone. And so this is widely used as a thermoplastic. Well, why thermoplastic is become very important compared to thermoset is that, as you can see, this we can make the thermoplastic composite very easily. How? Well, you just apply high pressure and temperature, and no time is very short, done. And also, reversely, we apply the heat, it can be plastic again. So we can redeform, recycle. So that's the characteristic of a thermoplastic. But compared to a thermoset, it's a chemical bonding. The bonding, cross-linking cannot be dissolved, cannot be broken. So which makes it strong, but reversely, they cannot be recycled. So this is just a simple overview, help you to visualize. And now speaking of the stress strain curve of the thermoplastic, and this is a strain and stress, and the all polymer chains, has the how they align, how the breather, the blue, the red one represent the thermoset, and the blue one represent the thermoplastic. So well, it shows the crystalline structures. Crystalline is the well-aligned the polymer chains, and there will be a amorphous and crystalline and together, and they can extend it and extend it. A very large large failure strain. So relatively, thermoset cross-linked, and the failure strain is the shorter, and thermoplastic, the failure strain is large, and strength-wise a little bit lower. While sometimes the this guy PEG or PEEK has the very high. This can be very high like this, even for the thermoplastic. How? Well, this guy, the crystalline and very special feature, this can be very strong. But no matter what the crystalline or thermoplastic, high temperature and high pressure, that's all in it. No time to wait for the chemical reaction. So imagine that we have a pure resin, okay, just a resin, and impregnate, and then we have a fiber. Imagine you have lots of fiber and the resin impregnate. Okay, this is the we mentioned about the tow. Okay, just the consider one small part here. Imagine there's a old resin, and then one fiber is just the put it in there, and then try to compare the property of the resin in this direction. So pure resin, the stress strain curve, there's very typical one for like the epoxy system is reaching the 70 megapascal and about the 2%. Now, let's say we have a carbon fiber in there or a glass fiber in there, then transfers in this direction. How the material property will change? Well, you may think, oh, these composite fiber there, oh, this is gonna be strong, this is gonna be good. No, because this will work as the inclusion and then cause a stress concentration, very bad. So that's, but transversely, this is the stiff, and then stiffness increase compared to this one. And but the strength will be decreased. Why? Because there are stress concentration, and then this will crack will initiate, and then this will separate fiber to fiber. This is another visualization you need to have. So again, transverse direction is weaker than pure resin system, but again, this one is really strong than conventional materials. But depending on the resin system, this can be behavior. The point I like to emphasize here is that this is the stress concentration. Now imagine this or that is the thermoset or thermoplastic. Okay, thermoset and thermoplastic, which can be better? Well, again, the thermoset and thermoplastic. And this is the thermoplastic. This is the thermoplastic, and same situation. And this is the thermoplastic behavior. And of course, this can be reduced, but A and B means that we have a higher, so less crack can be initiated, okay, compared to epoxy or thermoset. Why? Because the thermoplastic usually have the higher plastic strain that can release the stress concentration relatively compared to epoxy system, thermoset. Okay, so this is also important to understand. And that's why now imagine we have not just one fiber, but a lot of fiber, and the compare with thermoset and thermoplastic, and also imagine that there will be a void in there, and effect will be different. And then now, as a laminate, we can have a 0 and 90 and 0 and 90. So if we have a thermoset 090 or thermoplastic 090, the laminate behavior will be different, mainly because, okay, this is the say one laminate like this, and this, and we have a like that, and this is like that. So let's say this is a 0 and 90, and then we subject to like this. So this one will be very strong, but as I mentioned, this guy can be very weak under this load. But they have to deform together, so this guy can easily crack generate. Why? Because this one, if this is a thermoset, the failure strain is relatively small. So, but the fiber can extend it a lot, but this cannot extend it. But the laminate, they have to deform together. So 090 and extension, you can imagine what will happen to this guy, right? So fiber can be separate. Well, this sounds may okay, but there could be another load this way. Another load this way, it means that this can extend it this way, but now this guy can be a problem like this. So the thermoset, the crack can be relatively easily generated because of a small failure strain. But the plastic has the larger and extended well. Even though this guy doesn't support the load, this can extend it a large failure. So this is another advantage of a thermoplastic. Well, you don't have to understand everything, but I just want you to have a general idea about the thermoset and thermoplastic. This is the real simulation using the abacus modeling of random fibers in longitudinal, and this is transverse, and as you can see here and there, you can see a kind of a crack can be generated in multiple load. So ironically, each one thermoset can be stronger, but in laminate, the thermoplastic laminate can be stronger. Why? Because the crack can be delayed. Not always, okay? I just want to help you to visualize the role of the thermoplastic. Higher failure strain can contribute to composite structures. So there can be many plastic for the thermoset and thermoplastic and epoxy system and PEG and so on, and you know, all kinds of different properties. And then also resin. Well, in general, epoxy and polyester. See, epoxy and polyester is a very typical thermoset materials. And I will give you this slide, okay? But I just want to go through very quickly that the PA6 and PA46, PA66, we have many polyamide plastic. Good thing is this polyamide is the thermoplastic, and there can be very, very different plastics and material property, and you can see that. Again, I'm trying to give you an idea role of the resin system, okay, and the fiber and different resin system. We can have a very unique material property depending on the requirements. Say, oh, you like to have a very high strength of the impact, tension, and creep, or high heat distortion temperature, and the dimensional stability. So whatever requirement, you as a designer with the understanding of material, you can choose the fibers and resin system, also considering recyclability and etc. And so many characteristics. I don't want to, I mean, you don't have to understand everything, but you know, I want, you know, you as a future composite engineer, I want you to have some idea about the role of the resin systems. Well, this is the very old video. Imagine thermoplastic and toe preg, okay? Thermoplastic and toe preg. Okay, what does it show? Now each one has the one toe, okay? Now you can understand one toe. Preg, pre-preg. So toe and resin. Now resin is the thermoplastic. Now you can have can visualize the toe preg. What do you need to do to manufacture? Well, you need a press and temperature, right? So you need to apply the heat. Heat by the laser, heat by the you know, the a lot of heat source, even hot air, and then press. You need a press, compressive. Okay, so this makes the structures. Okay, well, this is not the all about the thermoplastic, but the I relatively like to emphasize the importance of thermoplastic. Why? A lot of issues relate to environment these days. So environment means that you need to consider sustainability of material, recyclability material, and carbon zero, net zero society. You heard many times. Now composite is being used, made of the plastic, and plastic, unfortunately, not recyclable, which caused a lot of issue environmentally. And to recycle, it takes a lot of energy, which is not good for the carbon free. So, for oil and gas application or any application, they like to use the thermoplastic, not just for the recyclability, but the processability and the very unique characteristic of a thermoplastic can be well used for the composite parts. Okay, so this is about the same, but I like to do a little bit different view, but it's the same concept. As you can see, structures. Now you can see open, the spreading, and fiber, and etc. Now you can better understand what this kind of slide means, and each one cross sections of one ply and the one toe 1.5, and then you can see how many the height, I mean the toe are orange, and 12K makes the 10 millimeter wide. Well, we made a little bit of mistake, but it doesn't matter. You can see the dimension of a 10 millimeter wide. Well, this is the one. And now this is the real pictures. I didn't make up, but this is a real cross-section of a fiber arrangement. Now, we like to analyze every single fiber. How to do that? Well, we better have this scale array, a hexagonal array, and diagonal array. This is the microscopic view of the arrangement of the carbon fiber. Now, like this, and then as you can see, when we apply all kinds of load, you can see this color represent and show stress concentration. This is not the schematic. This is a real simulations of composites. And you can see that depending on the load, you can see different color and represent how much stress can be concentrated in the fiber and resin system, like this, even one and the multiple, and you can see that. And you can have a model, different model, like the this is the scale and hexagonal, and the this is the we don't use it, but this is the diamond. So, well, this one, I just long time ago, when I did research, developed the micromechanics view. I believe that was the as a pioneer approach, and we developed micromechanical overview, the role of the fiber in the resin system. And we model like this, and then you can see these all the stress concentration. And this is the real measurement of polarized light. And as you can see, how well predicts. We have a epoxy resin and the fiber, and then locally there can be a very a lot of things can go on, and the usually, not always, as I said, the pure resin the strength will be say pure resin. Tensile strength is the Tm, and Y is the transverse strength is the Y. As I said, there it will be can be a stress concentration. So the composite, the transverse strength can decrease compared to a resin, but how much? Well, through all kinds of equation and etc. and theory, which was developed. Now we predict the 64% of the pure resin tensile strength will be the transverse strength of a composite. That's not always, but this is the another overview. So we can have lots of different micromechanical models, and the in FPM you can have so many the points. That is the same slide, like the random, and the we can have many different. Now random fiber is difficult to model them, of course, but you can imagine using the programming and to develop and like this, you can generate a random fiber. This is a real process of generating a random fiber. We can reach the like the 50% and 55%. Of course, this is a random. We cannot precisely predict a real arrangement, but you can generate as many as, but that's all the same fiber volume fraction. So this is the another numerical approach, and you can imagine the all the fiber and resin system, and then well, you can do a lot of stress calculation. And then stress is not uniform because the fiber arrangement are randomly distributed, and you can imagine the all kinds of stress. So this is the real one. We image processing, we get the really same as modeling, and you can, this is a stress of distribution. This is a purely numerical generation, and you can see this one, this is very much, they are in agreement. So that's the beauty of simulations. And so we can do a lot of research still, which can be very important, and the resin and the fiber. Okay, well, I don't want to go through all detail, but we will go back to this micromechanical overview again. So today, what I like to do is that to understand the look microscopically the resin and fibers and tolls and etc. Of course, later we will cover the how we do laminate sequence and analyze and stiffness and calculate how to calculate the price stress and etc. And composite is not just for the mechanical, but it can be exposed to moisture or many different media, and then it can also simulate. You know, this is the moisture distribution. Moisture distribution means that, you know, the in the exposed to the moisture outside, the moisture will smear into a composite, and then will degrade the material property of a composite, and this can be also simulated. So if you have a model of a microscopical modeling or random and understanding, you can do a lot. You can eliminate a lot of tests. And also, you can see the multiple laminate, microscopic, the multi-scale approach, each fiber arrangement with the different angles. And I like to emphasize that how much research and development can be done in terms of manufacturing process, in terms of design and so on. This one can be applied to many different types of a manufacturing process, winding, and the resin transfer or infusion, and so many characteristics. Okay, so I will cover up to here, and then I will select a slide. I will share with you, and then I will upload it. Well, if you have any question, please use the our cutoff, and then I will assign the task again through a cutoff. Okay, well, it's a 5:50 precise time to finish lecture. Well, not much time for feedback, but again, use the cutoff to freely communicate. Okay, thank you so much. And this second class will be also uploaded to our YouTube. Okie dokie, thank you, and see you next week.
네, 감사합니다.
감사합니다. 추석 잘 보내십시오.
예, 감사합니다.
감사합니다.
네, 모두 다 즐거운 한가위 맞으세요. You have a good time. Good time to study more on composite materials. Okay, bye.